Hello students, we are back. So, what have you established right now? Well, we've defined two new functions. We've defined one called arcsine of x, which is the inverse to sine of x with the domain of sine of x restricted to negative pi over 2 to pi over 2. We've also introduced arc cosine, we're going to continue to study, which is the inverse to cosine of x with the domain of cosine of x restricted to 0, pi. So, let's think about what this means. So if you say arc cosine of x equals theta, and I'll explain why theta is a good choice to use right now. Well, inverse arc cosine is the inverse to cosine. So this means that x is equal to the cosine of theta. But it also means more than that. So let's think about what this theta could be. So if you see cosine of theta is equal to x, that theta could be any number. You can plug anything into cosine. But what outputs are you allowed to see for arc cosine? Well, remember, so that's what is the range of arc cosine. So that'll be the same as the domain of cosine after you restrict the domain. So that angle theta has to be in 0 to pi. And of course, theta being in 0 to pi means the same thing as 0 is less than or equal to theta is less than or equal to pi. So let's write that down. For a valid input, an x value in between -1 and 1, if someone says that the cosine of x, inverse cosine of x, or arc cosine of x, is equal to theta, what they are saying is that the cosine of theta equals x, and this angle theta is between 0 and pi inclusive. Similarly, if someone says that x is in the interval from -1 to 1, and that the inverse sine of x is equal to theta, what they are saying is that the sine of theta is equal to x, and that angle theta, this angle theta, is in the range of inverse sine. What's the range of inverse sine? Well, you can see the range of inverse sine in the graph of inverse sine. What's the most negative y value you see? Negative pi over 2. The biggest y value you see is pi over 2. So that angle theta has to be between negative pi over 2 and pi over 2. And you should allow the chance that theta is one of those two things, inclusive. So let's use that to make some computations. Let's try to understand what the inverse cosine of 1/2 is, and in order to motivate why the questions that are asked before that are suited to answering this question, well, let's see that. So if we want to find cosine inverse of 1 over 2, then what do we need to find? We need an angle, call it theta, doesn't matter what you call it, but I'll call it theta, with cosine of theta equal to 1/2, and theta in 0 to pi, theta between 0 and pi. Well, we've generated a unit circle. Let's look at that unit circle and see if we can just see such an angle. Alright, here is that unit circle. So let's see if we can look at that and find the needed angle. So I want an angle where cosine is 1/2. So that's an x value. I need an angle where cosine is 1/2. Well, I see two different angles here where cosine is 1/2. I see this one, and I see this one. So next I should ask, are each of these between 0 and pi? Well, they can't both be, because inverse cosine is only allowed to have one value. If they were both in that range, then we would have a problem. Well, this one isn't, right? 5 pi over 3, that's bigger than pi. Pi over 3 is in the right range. So theta equal to pi over 3 does the job. So that tells me something. That tells me inverse cosine of 1/2 is pi over 3. And we can put that in now a lookup table. Inverse cosine of 1/2 is pi over 3. Nice. Let's do another one. Let's try to compute inverse sine of negative 1/2. So what does this mean? So I need to find an angle, which is between negative pi over 2 and pi over 2, with sine of theta equal to negative 1/2. Let's go over to that unit circle and see if we see such an angle. Well, certainly not in quadrant 1 do we see such an angle, so I'll take a moment and fill in the rest of this unit circle. I probably should have just saved one of the ones that I filled in at some point. Ah well, you already have yours. I'll pause and fill this in. Alright, we are back. Those things have been filled in. So these red traced ones are no longer relevant. So looking at this, what did we want? We wanted an angle which satisfies that sine of theta is equal to negative 1/2 and such that that angle is in between negative pi over 2 and pi over 2. That's the setup. So where do we see a y value, because sine is the y value, of negative 1/2? I see one there, and I see one there. Well, what angles correspond to that? Well, I see negative 7 pi over 6 and 11 pi over 6. So if both of those are in between negative pi over 2 and pi over 2, then I'm in trouble. That means that inverse sine isn't actually a function. Well, let's see. Is 7 pi over 6 between negative pi over 2 and pi over 2? No, it's way too big. Oh, but that's a problem, because 11 pi over 6 is, like, even bigger? So we need to remember that we can write the result of rotating by an angle of 11 pi over 6 in a different way. Instead, I can rotate backwards by negative pi over 6 and get the same output. The sine of negative pi over 6 is negative 1/2. And now ask yourself, is negative pi over 6 in between negative pi over 2 and pi over 2? And yes it is. So that means that inverse sine of negative 1/2 is equal to negative pi over 6. Inverse sine of negative 1/2 is negative pi over 6. And so now here's what I want you to do. Grab lots and lots of scratch paper. Do all the details that you need to do to fill in the rest of this table. So I'll wait. You go do that. Hit pause on this video, because I'm not actually going to wait. Do that, come back, hit play, and then we'll compare. Okay, we are back. So I'll think through some selection of them. You can skip through a chunk of the video if you feel very happy with that you filled out that table correctly. So I'll pick some at random. Let's suppose you wanted to evaluate both of the trig functions, why not, at negative 1. So to evaluate inverse cosine of negative 1, I need to find an angle whose cosine is negative 1. So there's an angle whose cosine is negative 1. It looks like an angle of pi will do the trick. Is pi in between 0 and pi? It is. So inverse cosine of negative 1 is pi. Inverse sine of negative 1. So I want to find an angle whose sine is -1. Oh, that should be 0, -1, shouldn't it? Well, by looking at your unit circle, where do you see a y value of -1? Well, you see one right there. And that tells you everything you need, right? So it looks like then your first guess would be an angle of 3 pi over 2, but 3 pi over 2 is not between negative pi over 2 and pi over 2. It's too big. So instead you have to rotate backwards by pi over 2. So inverse sine of -1 is negative pi over 2. Let's go to one where that subtlety doesn't come up. How about 3 pi over 2? Oh, there's an arrow, isn't there? That should be a pi over 3 in the bottom. And let's see why. So let's try to compute inverse sine of root 3 over 2. Inverse sine of root 3 over 2. So I want sine. So I want sine to be equal to root 3 over 2. There is a place where sine is equal to root 3 over 2. So it looks like I see an angle of pi over 3. Is that angle between negative pi over 2 and pi over 2? That is it a valid output for inverse sine? It is. It is. So pi over 3 is inverse sine of root 3 over 2. Let's do the same thing for cosine. So I want to see where cosine is equal to root 3 over 2. Well, doing that, let's see. Looks like that's here. I guess I also see one right here. But this angle, 11 pi over 6, isn't a valid output. It's not between 0 and pi. But this angle, pi over 6, is between 0 and pi. So inverse cosine of root 3 over 2 is pi over 6. Excellent. So with that done, let's, so those are basically all of the explicit computations that we'll be able to do for quite a while in this class. We'll do a lot of computations using a computer to assist us. You can ask a computer to compute inverse trig functions at inputs. Use a computer to find approximations. So let's do an example of this, an application of inverse trig functions. So one of the important uses of inverse trig functions is to take information about a triangle and use that information to determine other things about the triangle. So here's a setup. So here's a right triangle. It has a base of length 4, a hypotenuse of length 5. Let's try to compute the angle theta. Well, what do I know about this angle? Well, I can look at this triangle and see that cosine of theta is equal to 4 over 5. Moreover, this is an angle inside of a right triangle. The biggest angle you can see inside of a right triangle is, well, it has to be somewhere between 0 and pi. Oh, pi over 2, in fact. So theta is somewhere between 0 and pi over 2. It's an angle in a right triangle. So that means cosine of theta is 4/5, and theta is an angle that's in the range of inverse cosine. So that means theta is equal to cosine inverse of 4 over 5. And there is an exact answer. This angle theta is equal to cosine inverse of 4 over 5. And that's another way of thinking about what inverse trig functions are. As long as you take the inverse trig function at something positive, really what you know is that that's an angle that's living inside of a particularly arranged right triangle. So let's actually figure out how big that number is. Let's find decimal approximations. So again, I'll have a computer help me with this computation. Pause for a moment. Oh, well, I'm going to pause for a moment and come back with that computation. Okay, we are back. I have elected to use the Google calculator, and it is telling me that inverse cosine of 4/5 is approximately 0.64 radians. And when you don't specify a unit next to something that's an angle, I'll assume it's in radians. But let's also determine what that is, approximately, in degrees. So that's actually easy to do, right? How do you convert from radians to degrees? You multiply by 180 and divide by pi. So there it is. Well, okay, so I didn't tell Google that I was converting to degrees, so it still says radians, but that is what to do. So that means that the degree measure of this angle is approximately 36.87 degrees. Of course, if you're using a handheld calculator, you can probably switch from degrees to radians by hitting a few buttons instead of remembering the formula. Yeah, whatever. So there's an important payoff. If you know inverse trigonometry, then you can use inverse trigonometric functions to solve triangles. Right? I gave you this much information about the triangle. I gave you those two side lengths and that angle. And you could tell me what this angle was. Now, another neat thing is you could figure out the rest of the angles. You could now completely solve this triangle. You could find all of the facts about it. And we'll do that a few more times in a few other contexts. But right now, let's switch gears just a little bit, which means it's maybe a good time to break the video. So the next thing that I will do is I'll talk about computing trig functions at inverse trig functions. So I'll do some computations from the inside out, and we'll get some interesting results.